Hi and welcome. Thanks for joining us for the FEMAP with NX Nastran, an introduction to CAD Neutral Finite Element Analysis webinar. I'm Tom Harris and this is brought to you by Edge PLM. If you can keep your questions till the end, this will just respect everyone's time and allow us to get through things a little more efficiently. So let's get started. First thing you'll notice about FEMAP is it comes with quite a lot of commands on the screen. Don't be worried about this. These commands are there because FEMAP can do a huge number of things. It can do everything from geometry creation completely standalone from CAD through to completely mesh oriented and only mesh analysis, and then it can do CAD oriented geometry cleanup and meshing and analysis as well. So it can do a lot of things. All of it though is completely customizable, and some commands are there by default. Some commands you can tweak and set up as you want to do, and the entire layout is customizable as well. So first thing we want to do, we want to bring some CAD geometry in. However, we'll bring it in the neutral format. So you'll notice, I'll just show you some of the formats we've got. Huge variety here. Neutral formats, native CAD formats. We can also bring in models. This is finite element analysis models from a raft of other solvers as well. So you've got a lot of options there. Now we want to bring in this step file. So we'll just select it, bring it in, use the default options, and it brings it in very quickly and simply. You can give each solid a new color as I've done here. Now you'll notice that the solids that I've brought in here, it's a jib assembly, and it's all solid, very thin walled solid, which if you spent much time around finite element analysis, you'll know that this is not ideal because it produces either a huge number of tetrahedral elements or very distorted tetrahedral elements. What FEMAP allows you to do is extract the mid surfaces from these solids in order to use a plate or surface mesh. So we'll just come in and set that we want it to extract the surfaces for everything under 5mm and combine the tangent surfaces, and you can see this tangent surfaces or mid surfaces created. This then allows us to either hide or delete. I'm going to delete the original solids. So now we've got a combination of surfaces and solids, and very often while you're doing analysis, this is what you end up with. So I just wanted to do this kind of scenario to show you that FEMAP is still very, very comfortable with working with different element types, and it has all of the tools that you need to work with this. So now we want to go and create a mesh. First thing about creating a mesh is you need to assign properties. Now we generated these surfaces from solids that had the thickness. So FEMAP gives you a tool for re-extracting the properties of those solids into appropriate plate thicknesses. We need to select a material. I think, 1040 steel will do. It brings it in the units that you're working with, in this case millimeters, newtons, tons, and I want to give a different property for each solid thickness I'm working with. And if I come over here to the model info window, you'll see that both the material and the different properties are now created, and if I turn on highlight, you'll see that it gives me instant graphic feedback as to which properties are on which surfaces. So just quite a useful little tool. Now we also need to assign the properties of this end cap. This is a solid. We don't want to go and mesh it just yet. So what we want to do is we can right click on it and just select the attributes we don't have a solid property yet, so I'll create one on the fly. These tools allow you to work on the fly if needed. We've got a vast number of element types. In this case, I want to just choose a solid element. The property window updates immediately for a solid element type, and I'll just call this one solid steel, and I'll use the material that I've already used. If I want to create a new material, then I can just use this button here to create that on the fly as well, but I don't want to in this case. So now I just select and apply that solid to the end cap, that property to the end cap. So now I've created my surface properties. I need to create some connections before I do the meshing, but I can give it a mesh size. So I'll size the surfaces first. It goes and calculates based on the curve size. I can override that or use it, and then I can also use additional meshing options. For example, telling it to aim for a vertex aspect ratio of a maximum of 1.5, so that you can see the mesh sizes along the curves on the screen there. Next, I need to also size the solid end cap, so I'll just use the size on solid command. It also has a look at the curves. There's a lot more very small curves here. Again, though, I can override this, and again I'll specify a maximum vertex aspect ratio of 1.5 and say OK. It goes and creates the mesh size. So next we may even want to create a connection on the end, but before I do that I'll just turn off the mesh size display. Just keep the display nice and clean, and I'll create a connection, automatic connection, between the solid end cap and the beam. Now FEMAP gives you the tools for face-to-face, edge-to-face and edge-to-edge connections. I need an edge-to-face connection here, and it's got various options to enable you to get exactly the type of connector you need. And you see I've got one connector here that joins the face of the end plate to the edges of the end plate. So I'll just turn off the display of them because we don't need to see them all the time. And we probably want to create a mesh on the surfaces here next. So I'll mesh the surfaces on those two solids. Because I've already assigned mesh attributes, I'll use the meshing attributes that I've already assigned. If you don't want to use them, you do have a raft of options, but I'm just going to use the meshing attributes I've already assigned. And then I'll turn off nodes just for a cleaner display. Now, down on this end, we also want to join this beam to the base plate. And sorry, before I do that I'll just finish meshing. I'll create a tetrahedral mesh, and I've got the option of tetrahedral optimization. This just takes a little bit longer and gives you a better quality mesh. So for pretty much most models you want to use that option. Turn off the surfaces, and it's quite a neat and clean mesh all around that solid, nice and regular. Now if we come back up to this end, I need to connect the beam and the end plate, and often what happens in finite element models is the bolts get connected to the edges of a beam or the edges of a hole. Now this is not ideal. FEMAP gives you some extra tools in order to create effectively washers to share the load of the bolts, and these washers should represent about the diameter of the size of the fasteners. So we'll create a 5mm washer, and you'll see that it's very simple. Even though I've already meshed this model, I just have to select the edges to create the washer around, and it goes and updates both the geometry and the mesh and gives me very clean surfaces to work with. So now I'm ready to create my bolts. FEMAP comes with various bolted fastener systems. You can tweak any of these options, and with this one I've actually tweaked one of the hole-to-hole fasteners to make it a hole-to-hole surface fastener, which is what I'm going to use. So with this option, I first of all select a curve to define the diameter of the bolt. Then I simply select the surfaces under the head of the bolt, then the surfaces under the nut. So a three-step process, but quite a rapid way and simple way of generating my bolted fasteners. It creates a rigid body element, which you can see there, an RBE, on both the head and the nut and both ends of the bolt, and it creates a beam element in between the two at the diameter that you've specified in order to give you the correct bolting properties. So it's a very simple way of generating what can be quite a complex fastener system in a finite element analysis program. Now we've got our mesh, we've got our connections. I won't do any bolt preloads, but if I was going to, all I simply do is click on the bolt preload. I have to give my load set a name, and I actually have to specify the bolt region as well, which you can see. I specify bolt region, select the bolt element, which is the beam element in the bolt. I can use my query pick to select that, but I'm not actually going to in this case. I just wanted to show you that if you want to do preload, it is quite a simple option to do that as well. But now we need to create some loads and constraints onto this model. So we need to constrain the bottom face, and we need to load it by the hook. So I'll create a load on the surface. The surfaces that will be loaded are the inner surfaces of this hook area. So I select them, and if you need verification, you can always use the highlight option to check that you've got the surfaces correct. Then you can see down the left there's quite a number of different force or load types. I'm just going to use a simple force in the negative Z direction, 1750 millimeters. You can see it gives you a graphical indication of the direction and where that load is, and also the size of the load. Now, often we don't just want one load in an analysis. FEMAP gives us the option to copy loads. The first one would be, say, a lifting load. The second load might be a different load case. It might be lift with rotation. So I'll just rename the first load set back to lift, so that's all clear. And I'll edit the load in lift with rotation and just simply add a rotational component. The jib might be rotating or something, and this might add, I don't know, a 500 Newton load in the X direction, something like that. So you can see it's very easy to manage multiple loads, or load cases as if you like. We also have the option of adding a new type or a different type of load set, and that is what's called a combination load set. And this is simply a scaled combination of other existing loads. And you can see I can say, for example, I want to add a factor of 1, and then I'll scale the second load set by a factor of 1.5. And that is what's called a combination load set. Now, I don't actually need that in this case, so I'll just delete it. I just wanted to show you that FEMAP has those tools for advanced load set management, because it's very rare that an analysis is needed to be done with only one load case. Now, we also want to create a constraint. I'll just call this constraint set 1 on the bottom face just here, and this will be grounded, so I'll just call it that, and it's fixed in all degrees of freedom. You can see that it all shows up here. Next, we actually need to create an analysis. So basically I can click on analysis, and I haven't got an analysis set up already. I can create a new one. You'll notice I can create an analysis set not just for NX Nastran, which is the solver that we're using today, but I can create an analysis set for all various solvers that can be used with FEMAP. I've created just a standard static analysis set, except I want to change the load case or the boundary conditions, and I'll just delete the load out of this, because what I want to do is I want to set up two separate cases to be analyzed in the one analysis. And this is another tool with FEMAP to just speed up the processing time so that you don't have to spend a long time with doing your various analyses and reading and creating the results that you need to create. So FEMAP's got all of these tools. I've now got those two separate load cases, and then basically all I need to do is analyze this model. I do, however, have other options, and I'll just show you some of these. Some analysis programs will limit the number of processor cores you can use. FEMAP is unlimited except by your computer. So we've got all of the various controls that you need to optimize the analysis on your machine. Once we create or start the analysis, it opens up an analysis monitor, and this just gives us continual feedback as to what's happening with the solve. And you'll notice it then opens up a sparse matrix solver. With large models, this is very beneficial because it gives you an indication of how far through the solve it is. Now, ours is already finished, so I'm just going to go out and have a look at my results. I can just double click on the results that I want to look at, and I'll turn on the deformed model. This is an exaggerated deformation. Basically it exaggerates it by 10% so you can see the shape of the deformation. You don't have to view it as exaggerated. You can view the actual deformation if you want, which, to be honest, I normally do for reports and things like that. So I can see the actual deformation, and I'll turn on a contour, and I might just want to hide the element edges so I can get a clearer picture of the stresses through this model as well. Now, or I can also show you the undeformed model. Now, the undeformed model will never block the view of the deformed model. just so you can still clearly see what's happening there. So I'll turn that one back off. And you'll notice that the solid end cap is grey at the moment. It's not displaying the results yet because we're showing the plate top von Mises stress. Well, FEMAP can deal with multiple result types quite happily. So I'll switch that to solid. You can see the solid there. What happens if I want to view them all at once? Well, we can quite happily show multiple result sets at the same time as well. So that's showing the plate top. However, I also want to show the plate bottom because the stresses on each side of these plates might be different. And all I need to do is click on the double-sided contour, and you'll see if I turn that on and off a couple of times, you'll see the difference that it makes from one side of the material to the other. Now, to get a slightly clearer appreciation, I can also turn on the thickness of those plates just to give me a really clear visualization for what's happening in the stress on these components. So now I've got quite a good view of my stresses. I can turn off my loads and constraints so they're not blocking any of my visualization. I also have a number of other options. For example, I might want to know exactly where the maximum or minimum stress is, or both. I can do that. I just select which I want, and it gives me an indication of where the maximum stress is by labeling the node at which that stress occurs. So just gives me multiple ways of looking at my data and analyzing my data. So the next thing I might want to do is I might actually want to be able to have a look past the base plate. If I come up to my geometry, you'll see I can turn off the geometry very, very simply. However, this does not actually turn off the mesh. In order to turn off the mesh, I can just check or uncheck the various properties. Now I've got highlight on as well, so I'll turn that off, which is confusing things a little bit. This is better. So you can see how you can visualize only the parts of the model that you want to see. So I want to turn off the base and have a look in at exactly where the stress is, and you can see that the stress is just outside the bolt washer on that side of my component. Now that's one way of visualizing. I can also go in and let's just say I want to visualize the stress inside my solid. So how can I do that? Well, I have a number of options. I don't just have to look at a standard contour. One of my favorites is what's called an isosurface, and this breaks down the display so that I can just see a surface at each of the different major values of stress. You can see there I'm just looking at the stress contours, and it gives me a surface at each of the different stresses, which gives me a very good indication of the stress flow through this model. Another thing I can do is I can do what's called a section cut. Now this is a standard section cut, however with FEMAP it can become quite dynamic, and I can just scroll through my section, and obviously I can select different planes if I want as well. And so it lets me visualize. I'll just set the delta to be a little bit smaller. so that those on the other end of a slow connection can still see this clearly. And so as you go through, you can see the stress develop on the inside of the component as well. So that's just another tool for accurate stress visualization in your models. Next, I'll just turn everything back on. I've just got to turn off the section cut and turn on the rest of my contours. Back to a standard contour plot. Alright, I can also do things like criteria plots, and I can also do factor of safety plots. I'll create a factor of safety plot based on the first load case. It goes away, analyzes the factor of safety, and it actually creates a new output set. And then I've just got to switch to the appropriate vector, and you'll notice that while most of this model, or most of the solid, is very unstressed, if you like, some components of this model are below a factor of 1. Now, this basically means that FEMAP believes that that component will fail. So it's quite important to be able to isolate what areas are actually going to fail. And easiest way to do this is to use what's called a criteria plot. Now, because we're viewing factor of safety, I'm going to say below minimum, and 5's a little bit too high. Even that's a little bit too high. I'll bring it all the way down to, for example, 1, so I can see only the entities that are actually failing. And while it's not a large group of entities that are failing, this is pretty marginal, and I would probably want to review my loading in order to get this model how I wanted it and not failing. So I'll just switch back to my standard contour view, because I have another very useful tool, and that is report generation. Now I'll just switch back to the second load set. You can see where the stress is actually differing between the two, just by clicking between my different output sets. And I'm just going to generate a report. Now, this is a custom report because I'm lazy. I didn't want to fill in my user information every time. They are quite easy to customize. FEMAP comes with the programming interface built into it, so you can record actions, you can play them back, you can do all of that kind of stuff. Now, this particular one goes through, generates all your views, and lets you know that it's generated. You switch across to Word, it's all formatted the way I like it to be formatted, and the model hasn't been saved, so it tells me that. It gives me the information on where the geometry came from and when it came, so I can trace back every aspect of it. It tells me what geometry came in, the volumes, how I meshed it, all the various information you need to be able to validate whether this analysis has been done correctly. Gives me all the mesh information, material information. You'll notice I have not got a compression stress in there. The factor of safety we viewed was the tensile stress. If we had viewed compression, it obviously wouldn't have been able to calculate it. It's got all my load details, and then it gives us the plots as we had them laid out on the screen. We've got our stress and our displacement plot, and then it goes down into a breakdown of the maximum stresses, the analysis results for each solid, and the factor of safety for each solid. And you'll notice that the third solid has yielded, and it gives you an appropriate warning. Then it goes back and does the same thing for each material. So it gives you a material by material summary and a solid by solid summary, just so that you've got all the information you need to be able to make an accurate and informed decision. Now, obviously, we can also do our animations. We can save these out as movies. I'll just slow it down, add a few more frames so the guys on the other end of the internet will actually have something half reasonable speed to look at. And I can say whether it's loading and unloading, whether it's positive and negative, positive only, all of those kind of things. I've got all of the options in FEMAP to accurately and effectively visualize and communicate the results of these analyses to whoever needs to be communicated to. So that's just a very brief overview of FEMAP and some of the tools that we have to enable you to do quick and accurate analyses. So if you've got any questions, submit them now using the questions pane, or if you want to wait, you can review the webinar online later, email us or phone us. We'll just switch over now to take any questions.